Okay. Alright. Let me get started. Okay, so today has been a reasonably productive Monday, which is good, and I'm feeling quite drained already for the day. That's why I'm here to just squeeze that last bit of effort out of me so that I get something done before I call it a night. So today I have a few just few tabs of recent papers open. I think they're all released in like the last month or two, and yeah, I'm just gonna go through them. They are of course relevant to my area, even though some of them might be quite hard to understand based on what I can see from the abstracts, but I'll try my best to just at least get some idea of what they're talking about, and hopefully we get somewhere, right? Hopefully this doesn't take too long either, but that's what I say at for every reading stream, that it ends up taking forever. But that's because I keep searching stuff and I learn more stuff, and I guess that's not all bad. So I guess first things first, let's go for some music. I realize that I keep on picking the same music, and I think that the same thing's gonna happen, because why not? Okay, I have to pick. So annoying, I have to pick music that I won't get copyrighted strike from. What's a good reading music? Okay, let's pick this. I've not used this one, I think. Alright, so okay, this is a bit distracting actually. It's too fast. Okay, well, let's just make do. So I have a paper about some type of MCMC method that uses simplex. I don't know what I mean. I've never seen anything that does this for MCMC. There's this, looks cool. It's a really small paper, 7 pages, which is always fun to read. This looks interesting as well. Then there's this paper looks very interesting, even though it's quite pure theory and I definitely can't understand it, but maybe I can give it just give the introduction to read, and even if I don't understand it, at least I think it'll point me to places where I can find out more. And then there's this guy written by, I don't know who these are, Laura and Antonio. Poisson regression, right? I don't know much about Poisson regression, so I think it'll be interesting to see what this is really about, if I don't know if I want to. Okay, let's go for the smallest paper first. Maybe let's start with that. So this one, okay. Alright, reversible genetically modified mode jumping MCMC. There's lots going on. I don't really know what's happening. Wow, look at that look at that shorthand. GMJMCMC, right? Yes, like everyone's gonna call it that. Why don't they give it a name? I wonder. Why not just genetic jump? Okay, I don't know. Okay, let's see what this is about. This is just released a few days ago. Okay. Okay. Oh wait, there's another one? Wait. Unlike the earlier proposed, the introduced algorithm is a proper MCMC and its limiting distribution corresponding to posterior under reasonable regularity conditions. Right, so I think, is it their own work? Hubin, Fromlet, and Storvik, 356. Right. Oh, there's only 6 sites. Oh, and half of them is the same authors. I see. Okay. Alright, so I guess if I want to know more about genetically modified mode jumping MCMC. I can look for them. So if you're a research student or interested in research, sometimes when you find such specific topics, when the author has published quite a number of works on these things, you can sometimes even just email them. I think they'll be happy to know that they have readers and that people are interested in their work. And yeah. Okay. Functions of covariates are prohibitively large. What's this? What's a GWAS? Genome-wide association study. Okay, so there's genetic stuff. Okay, so it's not a proper MCNC in that the limiting distribution does not correspond to the marginal posterior of the model probabilities. Model probabilities. So when they say model, I wonder, do they actually mean like Bayesian model, or model, i.e., the variable, the parameter that you are sampling? Bayesian model selection, so it's about a model. Okay. Thus, only renormalized estimates of these probabilities can be obtained. Okay. Okay. Predefined correlated features. Then the general model space. Okay, I'm still a bit lost, but let's go on. I guess that's the thing with shorter papers, is that a lot of the background is it's not explained. Then the general model space, and so this is about the parameter. Okay, so you are choosing your model as parameterized by features? If there are correlations between covariates, what does that mean? Correlations between covariates. Okay. Alright. So this is like a discrete problem, because wait, I just realized something that I don't understand. 2 to the q. So you are literally talking about feature selection? Is it about feature selection? Like, as in, either it could be, well, right now I have two guesses. Either it could be, this is music is loud. Okay, either it could be that your parameters are discrete. I mean, they might be one and the same, but okay, either your parameters are discrete, or that you have a bunch of features that are there's too many of them, 2 to the q possible ways to select them. And then, I don't know, okay, let's just keep reading first. maximals size Q. Members of the new population are generated by applying certain transformations to the component. First, some components with low frequency from search space are removed using a filtration operator. The removed components are then replaced, where each replacement is generated randomly by a mutation operator with probability. So I guess this is, I don't know much about genetic algorithms, but I think this is kind of the main idea, is that you kill off the weak ones and then you mutate, and then so that you progressively get stronger over the iterations. I mean, I guess anyone knows that. Followed by a cross, probably PM by a by a mutation operator, PM by a crossover operator. What? By a mutation operator with probability PM, by a crossover operator PC, by a modification operator with PT, or by a projection operator with PP, where all of this. So okay, what? So okay, I think I need to look at the algorithm to understand what the hell is happening. Oh, there's delayed rejection as well. Oh, the algorithm. So okay. Yeah, I think I don't have enough to understand this paper on its own, but okay. Yeah. I don't know this. What is this? Is this like a progressive thing? Okay, so delay rejection. Wait, RGMCMC? Oh, reversible GMJ MCMC. Except if both preliminary accepted with mean and finally accepted. Yeah, I think to understand this paper I should read the original GMJ MCMC paper, and then I can understand this one. Maybe another day. Bayesian configuration selection and arranging complex regression contexts. Oh, this looks pretty complicated to me. Alright. Whoa, wait, what's this? 2019? What? Wait, have I read this? No, not the same thing, huh? How do I get the PDF download? Why can't I find it? Oh, download PDF. Okay. Anthony Lee, yeah, I met him at a conference a couple years ago. He's very nice. He gave me his dinner ticket, which would have cost like $100 or something. Wait, what's this about? Slow down by computational complex targets. Yes, we use a generalization of delayed acceptance. Device to reduce computational cost by a simple and universal divide and conquer strategy. The generic acceleration term stems from breaking the acceptance steps into several parts, aiming at a major gain in computing time that outranks the corresponding reduction in acceptance probability. I see. Each component is sequentially compared with a uniform variate. The first rejection terminating this iteration. We develop theoretical bounds. I see. Okay, clearly I don't know details, but right. Okay. Delayed acceptance is an idea that I haven't really explored much yet. I have used delayed rejection in my work, and I read a little bit about it, a couple of the important papers, but not so much on delayed acceptance. But I guess the idea is natural as well, which is to say that, well, in delayed rejection you have a sample that you are rejecting, and instead of just chucking it away and moving on with another proposal, you say that, okay, maybe we can do something, right? We compute a bunch of stuff, let's use them anyway for something else. So usually you compute a second proposal or further proposals, and then you hope to accept one of them, right? So that you don't waste all your effort. And overall, taking into account all the computational effort, you usually get some good gains from a delayed rejection type of scheme. And I guess delayed acceptance is kind of the same idea, is that when you have an acceptance, you don't stop there and you go, can we push it further? And you keep pushing it until it starts to become problematic in the sense that it's not getting accepted. Then you say, okay, fine, then let's just accept the furthest that we can do, which is kind of to stretch your computational dollar, so to speak. Looks like a readable paper. I am actually interested in this paper, and they're written by really good people as well. Also very diverse crowd here. We have medical stats people, we have economics, we have math and stats. Interesting. Okay, so we have that in the mix. Okay, let's read this one first. Maybe another small-ish paper. Okay. From Dublin. Okay, we consider sampling from the posterior. Oh, hey Cheeto, you're back. I have a paper for you might like. Check it out later sometime. Right, I don't know how to find the chat. Like, I'm seeing it on my screen, but I don't know how to highlight it. Do you mind mentioning the name of the paper? Like the title of the paper, so that I know. Otherwise, I'm just gonna try to write down the link. Sure, yeah. Okay, where are we? Actually, should I just read this one directly? This one looks much more relevant to me. What's this? What is it? VIC, variance, invariance, covariance, regularization. Oh, I think I actually heard about this paper. I've definitely seen the title. Unless this VIC is a very common thing that comes up. I remember seeing variance, invariance, covariance. It's kind of a funky name. Cool. Very cool. Let me read the abstract now. See what it's about. So, written by Jan LeCun, one of the greats. Got rejected by NIPS. Oh yes, yes. I think that's how I read about this paper. It was on his Twitter or something like that, where he said, or something somewhere, or Reddit or something. I think it's Twitter, where he said that this paper, like he's very happy about it, something like that, but it's rejected and no, whatever. Ah, yes, yes, yes. So okay, cool. So I'm not a expert. Yeah, Twitter. Yeah, that's right. So I'm not an expert in deep learning, but let's see what this is about. Recent supervised methods for image representation learning maximize the agreement between embedding vectors produced by the encoders fed with different views of the same image. Views, what does that mean? Like angles? Views. I guess some type of, okay, whatever, maybe some type of rotation or whatever augmentation technique. The main challenge is to prevent a collapse in which the encoder produces constant or non-informative vectors. Okay, we introduce Vicarage, I don't know, a method that explicitly avoids the collapse problem with two regularization terms applied to both embeddings separately. A term that maintains the variance of each embedding dimension above a threshold. Maintains the variance of each embedding dimension. A term that, okay, the variance of each embedding dimension. So it's seemingly saying that you are, okay, wait, I don't know what it's saying really. Different angles, right? So does that mean like a, what do you mean, like taking pictures from a different angle, that type of stuff? Which I guess make a lot of sense, because when you get pictures of, say, cats and dogs, it's always gonna be in different angles, and you want to learn that they are all the same animal. And a term that decorrelates each pair of variables, unlike most approaches, does not require techniques such as weight sharing between the branches, batch norm, feature-wise norm. Oh, you don't need? That's interesting. Output quantization, don't know what that is. Stop gradient, memory banks and achieves results on par with the state of the art. We show that our variance regularization term stabilizes the training of other methods that lead to performance improvements. Okay, that's interesting. Yeah, you want to have a strong representation using views of, that's right. Okay, that makes a lot of sense. Huh, it's rejected by NIPS. That's funny. Pity though, I mean, it's such a fancy title. Would have been cool. But anyway, cool. Right. So well, I mean, if you have the time, I guess I just have some basic questions about just the general area, because I'm not super familiar. But when they say embedding vector, I'm guessing what that means is the output of the encoder. So you take your image, which is something like a bunch of pixels and then a bunch of channels and whatever, and then you put it through an encoder, squishing it down to a small dimension. And would that be called, is that what you mean by the vector? Or yeah, the encoding output. Okay, so that's kind of generic, like encoder stuff, right? So what does non-informative vectors, what does that even mean? Why would a constant vector be non-informative? Has it to do with probabilities or something? Because that's how I understand when the word non-informative is used. Or maybe it's just easier that, if I should just read the thing to figure out what I don't know. Okay, yeah, you got your encoder, you got your decoders, I guess, and then S would be your minimized distance between bring covariance to 0. maintain variance. Random transformations. Ah, I see. So you take one picture, you transform it randomly a bunch of times. I guess this tree, what does this tree mean? The tree channels? What is it? Okay, so you basically get two corrupted images. You make sure that they agree with each other. Okay. According to my intuition, if your embedding dimensions is too high, you will end up with vectors that aren't as informative. What does informative mean? Okay, I guess informative I see what it means. Collapse, right? So meaning to say you end up with the situations where many images give you the same output. That's what a collapse mean, right? And then you can't tell apart them, and then there's no information. You lose information from that. I guess. I mean, I feel like I'm in the right ballpark, right? Even though the details are probably not very sharp, but okay, this is cool. And the way they enforce that is such that they maintain a variance so that things cannot be the same. They must be somewhat different. That's an interesting take. But you bring the covariance to 0. Covariance to 0 meaning to say each of the components you want them to be as independent as possible. So as you want them to hold as much information as possible while preventing collapse. Okay, I mean, I guess I roughly know the goal of this thing. Yeah, I read about this title. Wow, look at all these people, all cited within the past. This is just past 2 years. Damn. Oops. What did I just do? Yikes. What did I just do? Very cool. Yeah, that's cool. But why? Interesting. Wait, why would things collapse naturally? So if you have too high a dimension, why would things collapse? I thought too low you would have. I don't know. Maybe I should read those. But yeah, I don't know most of these things. That's why I feel like it's gonna be so lost on me. Okay, let's read the intuition part maybe. The mean square distance between the embedding vectors in variance. A hinge loss to maintain the standard deviation of each variable of embedding above a given threshold. This term forces the embedding vectors within the different batch to be different. Right, that's right. So you penalize them if they are the same. Interesting idea. Wait, what's a hinge loss? I don't remember what it is. Oh, it's just okay. Okay, so it's just 1 minus t times y. So maximum margin. Okay. And a covariance term that attracts the covariance over a batch between every pair embedding towards 0. This decorrelates a variable to prevent informational collapse. Interesting. Very interesting. Cool, thanks for the share. Yeah. I don't think I can understand too much from this, but I think it's already quite good that in the past 2 minutes I figured something. And yeah, when I need to, I can definitely come back to this. All these terms are lost on me. Cool. Very nice. All right, thanks for the share. Yeah, I think I'll come back to it when I need to. Let's check out. Okay, let's see how far we can take this paper. I don't know. So two-stage, we examine adaptive MH, which employs adaptively tuned Gaussian process surrogate model at the first stage to filter out poor proposals. Oh, if a proposal is not filtered out at second stage, a full and expensive log likelihood, oh my god, log likelihood evaluation is carried out and used to decide whether it is expected in the next stage. I see. Introduction of the first stage constructed in this way saves computation on poor proposals. But does it... But then would it be correct? Would the algorithm be correct? Because if you just ignore it, will you still be targeting the right things? A key contribution in this work is in the form of the acceptance probability in the first stage obtained by marginalizing out the GP function. Oh, what? This makes the acceptance ratio dependent on the variance of the GP, which naturally result in an exploitation trade-off similar to the one in Bayesian optimization, which allows us to sample while learning the GP. Whoa, I don't know what this means, but I try. We demonstrate that using this expectation serves as a useful filtering scheme. The second algorithm is a two-stage. Wait, what? There's two algorithms? Two-stage algorithms. Okay. The second is a two-stage form of the Mala. Here we use GP as a surrogate for the log likelihood, but in this case the GP is used to approximate the gradient required. It's also used to... oh. The gradient of a GP is also a GP. Yes. Oh. Interesting. So it's saying that it's correct because it can marginalize out the GP. Okay. I feel you. The approximation we use is log likelihood of the data given the parameter is a log probability, log likelihood. What is happening here? Whoa. Okay. Is roughly equal to the GP with mean and kernel, some theta star and IT. I don't know what IT is. Current sample, and then there's a star here. I don't know what that is either. Okay. Full T set of T full evaluations of the log likelihood by the current iteration. What do you mean T? What is T? What is T? Time? Number of data? What is it? Not stated at the moment. What are they trying to improve on this paper? The efficiency / randomness. I think what they're trying to do is to... So the point is that well, maybe you'd be familiar with log likelihoods. So if you have a large data set to compute a log likelihood, you will need to compute the model forward and then find the probability of the data arising from the parameters. And if you have a large data set, that's very expensive, and that's one of the main costs in algorithms such as MCMC. And so right now what they're saying here is they're proposing this two-stage thing where the first stage they filter out poor proposal. So if it's bad, I yet to see how they define bad. If it's that case, then there's a good chance that it won't be computed with the full thing, with the full model. So you save cost, and if you save cost, that's overall you increase the efficiency, right? Cost efficiency is more or less your kind of your output over your cost. So that's what it's trying to do, I think. Yeah. And then it's also doing another thing by using a surrogate. Yeah, so GP is a cheap to compute model, and GP is it's a very nice model to work with because it has a lot of nice Gaussian properties, and you can do very nice things like marginalize and whatever. Yeah. Right. Okay, I'm trying to see how fast I can read this, because anyway I can't understand too much. So, and I'm still trying to correct my bad habit, which is that I try to understand too much from each paper, whereas that's really not the point. If I can spend half the time and get 80% of what I would have gotten if I spend the full period, I should just get away with 80% really. And who knows, if I read more faster, when I come back my second cycle, I could understand it much faster. So should not try to get too hung up on these things sometimes. Okay, so T-food evaluations, the set of T-food by the current iterations, and collecting denotes parameter value at which these evaluations were made. Okay, this is interesting. Okay, so these were all the previous values computed. So you basically you so this is a cache, right? That's a cache, right? You just store things. Adaptive tuning of the GP surrogate is accomplished through the use of collection of I or full evaluations. So the GP is gonna grow? Is that what it is saying? Okay, wait, I don't know. Because this collection is gonna get larger, right? I don't know. Okay. We argue that the tuning schedule we suggest satisfies diminishing adaptation, and hence will correct ensure. Oh, okay, that's important. That's very, very important. Within the Markov chain, there has been much interest in recent years, blah blah blah. Yes, that's true actually. I also spend way too much time trying to understand every single thing, which has led to a huge backlog. Yeah, welcome to the club. Yes. Yeah. I guess depends on what you want out of the reading, you know. If it's a completely important paper that is the, you know, the important landmark papers of your area, then might be good to really break the paper down and understand every nook and cranny of it. But for the most part, you know, yeah, learning to filter, that's right, yeah. But for the most part, that's not necessary. And the thing is, sometimes even if I spend so much time understanding it, when I come back 3 months later, I don't remember it anyway, or I don't remember the details anyway. Okay, target measure from different aspects. Approaches using noisy or invariant transition kernel have gained much interest. Yes. Okay, yes, expensive likelihood. So yeah, expensive likelihoods is a huge research area by authors, and the results. The results, what do you mean? Like good and bad? Is that what it is? Or like where they claim to be super impressive results? Is that what you're saying? Because interestingly, I don't really filter what I read by the results that much. Or maybe it depends on the area, because I guess in deep learning, if people are trying to all the time beat the state of the art, then that could be one of the main point, or rather main attraction of a work. But for my area like statistics, a lot of the time I'm reading because it's new. It's a new method. It's a new technique. Even though it doesn't work super well for all problems, usually it's valuable to read it. Like I said, the results, right? Right. Actually, I have a question. I mean, it's kind of the standard nowadays that everyone tries to bring new methods to train your network or whatever. Add a new term, take away a new term, use whatever data augmentation techniques, blah blah blah. But a lot of the papers that I see, which is not that much, but they all claim to beat the state of the art, or at least close to it. So I don't know. Is there many papers that come out that says, oh, actually no, we don't beat anyone, we just like, hey, just a method, or like we have something. I don't know. It feels like everyone's beating the state of the art every day in some way. Okay. Like lesser parameters but close to SOTA. Yeah, that's right. There are papers that introduce a different metric. Yeah, okay, yeah, I think that would be valuable, right? That would be very valuable if you achieve close to state of the art, but with much simpler setup, or much cheaper, or it's more robust, blah blah blah. That's very valuable. It's true. That's a good point. That's a good point. Okay. Okay, now we're into the method. Alright, here we go. We combine the Metropolis Hastings with a GP model at which approximates the log likelihood. So again, this is saying that your log likelihood is a GP, approximated by a GP, parameterized by a mean and a covariance or kernel that is parameterized again by your this is getting dense by your parameter values, condition on all the fully evaluated log likelihoods. I've yet to see what this does, but alright. Can be used for pre-filtering. Oh, so this is not actually a new idea. So you use GP to approximate the log likelihood. Okay. GP is based on a collection of yes. A proposal is made from current state and then the usual MH acceptance is computed using the approximated likelihood. If it is accepted, it goes to the second stage where another acceptance is computed, but this time based on the full. Oh, huh. Okay. Oh, that works. Interesting. That works. Why would that work? I guess. Why would it not work, huh? Deep learning research is so saturated, man. I think other fields might have easier time filtering. Yeah, that's true. That is actually one of the reasons why I did not choose deep learning as my main subject area. It's just that, yeah, I don't know. I mean, you refresh every half a day. There's like new things, and it's pretty intense. And I don't want to. And at least for myself, I wanted to really take my PhD time to learn properly. I don't know how to say, like, I wanted to learn a lot of properly things and not spend too much time just chasing numbers and, you know, hand tuning things or tweaking, I don't know, tweaking parameters to get that nice, you know, nice result. Yeah, it's a bit too intense for me. But yeah, it's pretty saturated. Yeah, I agree. Okay, SK denote the point sample up to iteration k. Okay. Wait, SK? So this is the most recent element and denotes the proposed state. Alright, that's fair. Yeah, most of the time it's just better results, you go burning more money, which is sad. Yeah, I agree. I mean, again, it depends on the goal, right? You know, if the goal is to find that one specific setting that can solve your problem, great, right? Power to you that you found it, even though it could be just a local minima or whatever, doesn't matter, right? If you found a setting that can actually help you drive self-driving car safely or whatever, perfect. But as a discipline, yeah, unless you are Google or Facebook and you have, you know, thousands of super TPUs running, it's gonna be a tough time. Yeah, which is why I'm really impressed by those people who can get a lot done, like by the time they graduate. It's ridiculous. Like they have like written 20 papers and wrote a book chapter, gave 40 talks. I'm like, what? Where did you get the time? Yeah. Highly driven individuals, I suppose. Yeah. Very, very competitive area, yeah. Let's just hope these all translate to, you know, real good uses in real life and not just really chasing numbers. That would be truly the sad part if it amounts to not much. Like at least I would say, you know, like maybe for statistics or whatever, even if you don't get fantastic state of the art, you know, the methods that you devise would be valuable, you know, 40 years, 50 years, thousands of years later, right? It would be true. It's just math. Yeah. But if the method is based on tweaking parameters based on a specific data set, I mean, unless the data set is super important and worthy, man, that is just very, very tedious hard work to somewhat overfit. I don't know. Oh, we have another person, Kiwi. I can't see the name. Kiwi Gimaro Mania. Hello. Good thing I have no idea what you're doing. Yeah. Well, I don't have much idea as well, but I'm reading a paper that has to do with statistics. So I'm a research student. Yeah, whenever you see me here, it's mostly because I feel lazy and I need to get work done, so I put myself here. Definitely techniques that revolutionize certain steps, transformers, change everything. What topic first? Yes, statistics, yes. Computational statistics, so in short, algorithms that are based on probabilities. I guess that's the main takeaway. Yeah. I guess when people think about statistics, they might figure it's about, again, depending on your background, I guess the most layman would think it's about, I don't know, scatter plots and charts and people using Excel. Hey, unfortunately I can't read Korean, so I don't know what those characters are. Yeah, I think of the normal distribution. Oh yeah. Well, that's good. It's good. Yes, the normal distribution is actually, yeah, if you think about it, it's a little bit of a joke in statistics, is that a lot of times we make a lot of normal assumptions, which is true in some sense and in some situations, but not all the time. Very hard. Very hard. I'm just going to DS and ML and just trying to find what I need to learn. Oh yeah, cool. Yeah, I mean, well, so my research supervisor is, his background is in math and statistics, and right now he does a lot of machine learning and deep learning, and he teaches data science courses. So the fundamentals of data science and machine learning is definitely, it's just a few important things. You have statistics, you have your, obviously statistics entails some calculations and calculus, whatever. Linear algebra is massively important if you want to compute anything on a machine. And yeah, there's also a lot of AI theory if you're into that. Yeah, like decision theory, those type of stuff. That's quite a different area, I think, in terms of application. How much do I get to know? If I go deeper, I'll probably have to know more, probably, to get started. Well, okay, again, I'm not a... Wait, so that means, when you say you're getting into ML, like, are you starting to self-learn? Are you going to take it as a course in school, or... But for basic stuff, I don't think I need to know all the stuff from the beginning. Self-learn, yeah. So, well, maybe one important thing is, what is your goal out of this? Like, what do you want to use it for? Some project that you're doing? Or would you like to, really try to understand the area for some deeper purposes to get a decent job someday? Okay. So let me just put it quite straightforward. If you want to, let's say, if you want to design, create a neural network, I'm planning to get higher studies in math. Wait. So right now you are pre-college, I assume, or have you graduated college and you're trying to do more? But yeah, yes to which one? Sorry, I'm not following. Pre-college. I see. Oh, okay. Well then, no. Well, first and foremost, you're already in a good place, that you're already doing well, in the sense that you're looking to learn even before you start college. I only learned most of what I know after I graduated college, before my PhD. So I'm only a few years into these stuff. So that's good on you. Yeah, you it depends on how much mathematics you know. If you want to just write a neural network let's say to identify handwritten digits, which is like the most basic thing in any AI project, you can do that in 10 lines of code. Let me put it this way, right? You can do that in 10 lines of code without any understanding, right? You write, you understand what the code does, 10 lines of them, and then you boom boom boom, everything comes out, you get very good results. But so if that's what you want, then what you should do is to dive straight into the libraries that you want to use. Learn a bit of programming, learn TensorFlow, learn Keras, whatever. Do what you want to do with it. But when you do that, naturally you don't understand what's underneath the code, right? You don't know what data really is, you don't know what models are, you don't know what optimization or inference really is. So depends on what you want to get. You can go different depths. Yeah. So right now what you're looking here, I would say from all the way from not knowing anything and applying things to all the way down to mathematical theory, this is something in the middle, I guess. My goal was to always understand what is black box. Oh, okay, well, first of all, I guess the way, I mean, if you're using the word black box, I guess you already have a good understanding of abstraction at least, and how deep things can get maybe in these type of area. Yeah, so I would suggest the most basic thing is to start with a bit of linear algebra, because you need to understand basic things like vectors. The most basic neural network requires working with vectors, matrix multiplications, things like that. Have a good grasp on that. If you can code, that's all the better. All the better. Pure math abstraction is not a new thing to me. I have a friend as a right. Okay, yeah. I mean, pure math people, they are really impressive to me. So yeah, they learn completely abstract things, and it's remarkable. Yeah, I'm trying to learn more pure math, every time I read these things, but it's tough. Yeah, I do know quite a number of pure math people trying to get into data science after they graduate, and then they can transition quite well, because just the mental agility that they get from what they do is quite applicable. And my own supervisor is a math major before he did his grad studies, I think. Yeah. I hate reading equations. Why can't everything be in Python? Aha! I think that's that's the sign of a computer scientist right there. Yes. Just yesterday, I was helping out a friend with a math problem, something in calculus, and I was trying to look at the equation and understand how the curve looks, and my friend just says, "Can I just plot it out in MATLAB or something, and then just look at it?" But I'm like, no, you can't do that. And yes. So interesting question, Cheeto. I have this question for you. Maybe it'd be interesting, or Kiwi or Korean characters, if you're interested. So the question is quite straightforward. When you write all the numbers from 0 to 99999, so that's 5 nines, or 6, doesn't matter. Let's say 5, so 0 to 99999. How many times does the number 0 appear? No, how many times does the number 1 appear? Yeah. So for example, the number 11111 has five ones, right? And 1 2 3 4 5 has 1 1. So if you write everything from 1 all the way to 99999, how many ones there are? Yeah. So a friend just sent me one line of code to solve it, which is just a basic for loop and some basic function. That's funny. It's like boom, done in 0.2 seconds. Let me get a paper. Oh yeah, go ahead, give it a shot. It's a very interesting problem. It's a cute little brain teaser. Okay, I was about to write in Python. Oh, I mean, go ahead, sure, yeah. But I would advise that there's a method to it that does not require coding. And that method, interestingly, should take you, less than a minute. So it's not a brute force problem. Sure, yeah. I apologize if I'm not here later, because I probably have to leave relatively soon, in the next hour or so. Oh, but don't apologize. Thanks for dropping by, and hope you have a good day. Think about the problem when you're bored. You can look up the solution online as well. I'm pretty sure it's online. I found it somewhere. I don't know. I can't think of the solution. Can you explain it? Okay. So here's the solution. So the idea is to find that is to find out the trick, right? What's the trick behind it? So the first thing is that I don't know, let me just write out somewhere. Let's first write everything as 5-digit numbers. So 1 will be 00001. Okay? Right, so everything is a 5-digit number, right? 99999, that's a 5-digit number. So first thing is to realize that by making this augmentation, the solution does not change. Okay? Because let's say you're talking about the number 10, right? It would just be 00010, right? The number of 1 is still 1 here. You are adding more zeros and you're not changing anything else. So the number of appearance of 1 is still the same. Okay? That's the first step. Is that obvious? Right. Okay, so everything is a 5-digit number. That's the first step. Okay. Yeah, makes sense. Okay, cool. So now the next step is to realize that how many 5-digit numbers are there. If you include 0000, let's say, that will be 100,000, right? From from all zeros to 99999, that's 100,000 numbers, 100,000 digits. Okay, so the digits. 100,000 numbers where each of them has 5 digits. Right? So, there's all 100,000 numbers. Each one of them is a 5-digit number. So to write all of them down, you need 500,000 digits. Okay? So 500,000 digits to write down everything. Okay. And then the last step is to realize that all the digits occur with the same frequency if you include 0. Right? So 0 appears the same number of times as 1, appears the same number of times as 2, and 3 and 4 and 5 and 6. Right? Everything, after all, from 0 to 9, everything appears once and everything appears once again. So each time you get the same, it's the same solution for all the digits. Right? And you have 10 digits in this case, which is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 digits, and they all appear with the same occurrence, which means this 500,000 digits is the total digits necessary. And if all of them appear the same number of times, you divide by 10, and you just get 50,000. So the number 1 appear 50,000 of the time, 50,000 times. Yeah, that's it. So you're using using some symmetry in your argument. Yeah. So this trick works for all the digits except for 0, of course, because if I ask you how many times does 0 appear, then you need to think a little bit more, because now that if you do the first step where you convert things into 5-digit numbers, you add extra zeros, right? That's why you can't apply this to 0, but everything else is the same. Yeah, so it's a nice, neat little trick. All right, let's carry on here. Okay, so likelihood. Yes. We use a noise-free GP as a surrogate model for the likelihood denoted by the posterior GP at the K condition on the I. We use LL to denote the GP distributed log likelihood. We choose parameters to satisfy the following. Why is it so warm? Hmm. Okay, so you're learning the GP as well. Yeah, I'm not. I mean, yeah, I don't know too much about GPs actually. Okay. So yeah, the more you compute, the better your approximation is. That's the main idea, because your posterior GP is conditioned on all the log likelihoods that you have computed in full. The following interpolation property. Okay. The mean function and covariance, the prior mean and prior covariance of the GP selected to guarantee exact interpolation is that your mean condition on I at theta is your log likelihood, which is your full log likelihood, right? Yes. And then your covariance is 0. Okay. So this is the prior. For all I with a corresponding entry ith. Yes. Any universal covariance function satisfy this property, for instance, squared exponential. Okay, so wait. So you don't have to use 0? I don't know. Wait, 0 means that there's no noise. I mean, I guess this what is this what I mean by noise-free GP? I don't know. That means you are just saying that this is your starting point. I don't know. Maybe I should read more about GPs. They seem to be more. They seem to come up more and more. Even in deep learning, I see a lot of GP stuff. After all, I think there's a theorem that says that any neural network can be the limit case of a neural network. I think that's infinitely wide or something like this is a GP. So GP in some sense is a continuous version of a neural network. Something like that. Is it? GP continuous neural network. Something like that. Deep neural networks as Gaussian processors. This paper looks relevant. It's cited 500 times. Surely it's useful. Yeah, I guess it's something along those lines. Alright, let's carry on. This means the prediction of the GP at points are exact and certain, which is a desirable property in the noise-free regression problem, I guess. Use the predictive posterior GP condition on the collection I to approximate the log likelihood. Define. Wait. What do you? But this is. Oh, Ian Murray. What's the term to? Right. What's the updated GP? Is it this? His titles are huge. Let me just recap a little of GP just so that I recall. I thought I know what they are, but it seems like I've forgotten a bit too much. Okay. Yes. Um. So what would be the posterior here? Yeah, I should really read this book. It's a really pretty book. I don't own it yet. I should maybe go buy it. I have some book funds to use anyway. I actually did GP before. I have code on it. Maybe I can find it. I must have code on it. Oh, this is from forever ago. I don't even know. Miscellaneous Gaussian process. There we go. Oh my god, I wrote this what 2-3 years ago. I don't even know. Oh my god, that oh my, wait, did I write this? I must have, because only I would leave something stupid like this at the end. Alright, let's see if I can learn from myself. Yes, 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 yeah, yeah, okay. What's this build domain? What did I do? Conditional. Ah, yeah. Filling in the covariance matrix. Sure. Given observed data, compute conditional mean and variance at position B. Ah, there we go. Sampling from a GP. We use RBF. Oh my god, I'm thankful that I wrote this. The magnitude controls how much moves away from the mean, while the length scale controls they are affected by its neighbors. Different value as yes. So okay, so this would be for length 1, sigma 1, then this sigma 5, and then different length scale. Alright, no, these are, I understand. Yes. I wrote this down before, like the whole derivation in my first year, I think. I don't remember anymore, but yeah, preconditioning preserves Gaussian distribution. The conditioning preserves Gaussianity, sure. The posterior is also a GP given by. So this is a little bit complicated, but let's just see what it involves. So the mean requires your data y. Oh no. Wait, YA is distributed as. Wait, why is this YA here? This is not right, is it? Looks wrong. Looks wrong. Yes. XB minus. Oh no, that's correct actually. So A, B, 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 mu A, and mu B. I think that's correct. Because my mean is 0, so I can just do this. Covariance. So I need the covariance. Wait, I'm a bit confused. What is YA? Yep. So I need the covariance matrix between the data for the data itself, and that will give me the covariance of this GP. Wait, I'm still a bit confused. Okay, let's just look at the code. We want to perform inference on this function. Posterior GP print test mean. So I have all these points, and then my GP predicts this. Okay. Okay, I mean, sure. It's super basic, yeah. But what is this? What's this term? I don't believe it. I am confused. Okay. How do you condition? I'm too lazy to write it out. Yeah. Yes. Dude, I swear I know this song. How am I picking a new video that I've never used before? And I'm getting the same song. Maybe they are all the same songs. Okay, whatever. Does not matter. Okay. Yeah, the Gaussian predictive. Alright, here we go. So that was a noise-free case, by the way. So this is the noisy case. What is this nonsense color? Who the heck did this? It's a bit hard to read. So the predictive distribution is this. Let me try to get this one right. Not convinced. Is the higher goal generalization? What higher goal? Like the GP? Is that what do you... How do you condition? Oh man, I'm so tired to think that I don't want to figure this out. I just want to find a correct source. No. Yeah, kriging is like your research. No, my research is, well, maybe, but so right now I'm working on a sampler that uses ideas of sampling on the manifold, and to do that you need a constrained version of the sampler, and what I'm doing is in some sense generalizing, but not in the theoretical sense. So I'm trying to generalize the method so that it can be used for more classes of problems, right? But in general, what the goal of my research is essentially efficiency. So I'm trying to devise methods or figure out ways to make methods cheaper and more flexible. Yeah. Yeah. So I guess it's like applied probability or applied statistics. But I still don't know how to use Stata or Excel, so never could figure those things out. Very complicated to me. Much worse than coding. I see. Yeah, yeah, yeah. So the probability of y given f, where f is your observed values. Yeah, okay, yeah. So that's what's wrong with my code, with my note here. That this is not YA, this is Y. Should change it. Wait, but why is it called YA here? Maybe this is not here. Like this. Something like this. But the mean yeah, so Y is observed data. Yes. Okay, now this makes a lot more sense. This would be covariance minus the outer product. Wait, this is different values? I'm not convinced. Ah, yeah, it's the same value. So VB minus V dot dot dot. Yeah, okay. Yeah, okay, so this makes sense, right? So the new data is dependent on the old data, and then you do a bunch of stuff. Yes. What is params? Oh, params is the length and sigma. So what is the B and A? Locations, right? So it should be locations. Yes. And the covariance is given by your kernel. Ah, that's right. Now I remember. Oh, what is this? What did you write? There's a lot of stuffs. Oh my god, I don't know how to find a place to read it. Okay, if you can, you should look at neural distillation. It is a range of techniques that try to distill knowledge of a large model into a smaller model. You might actually advance the area because barely anyone's working on it, I feel. Ah, I mean, sounds good. Distillation. Never heard of this specific term. Geoffrey Hinton. Oh, relatively, well, I shouldn't call it recent. In statistics, I mean in AI, I think 2015 is ancient, probably. Knowledge distillation. Cool. Distillation, I mean, this looks like it's gonna be a chunky ass paper, but let's see. No, it's 9 pages. Great. A simple way to improve the performance of any algorithm is to train many different models on the same data and then average the predictions. Sure, unfortunately making predictions using whole ensemble could be cumbersome and maybe too computationally expensive to allow deployment of large number of users, especially if the individual models are large neural networks. That's true. Caruana and his collaborators have shown that it is possible to compress knowledge in an ensemble into a single model, which is much easier to deploy, and we developed this approach further using a different compression technique. Ooh. We achieved some surprising results on MNIST, and then we show that we can significantly improve the acoustic model of a heavily used commercial system. What? By distinct knowledge. Okay, I don't know what that means. Acoustic model. Okay, doesn't matter. We also introduced new health ensemble composed of one or more models and many. Interesting. That was the last good paper on this area. Really? What? Something's wrong then, right? Why? I mean, this paper has been read at least, I mean, has been cited 7,000 times, so it's been read at least, I guess, 10 times that amount. So why is it not worked on? Either it's a bad idea in the sense that people tried and failed, or it's not called this anymore. Maybe it's just developed into another name. So when I hear distilling knowledge, like what you described by you know, distilling knowledge, it feels like is it like a transfer learning thing, or you know, does it go by a different name? Maybe it's representation learning. But this is cool. Yeah, I'll take a look at this later. Yeah, this is cool. Interesting idea. I've never came across this. Thanks for the mention, by the way. Oh, this is even a term. It's a proper term that people talk about. Transferring knowledge, right, is from a larger model to a smaller one. Okay. Okay, seems like this page seems like just a reiteration of what the hell is an acoustic model? Oh. So it's literally just audio models. Alright. Representation is learning is different. They aren't using big networks to represent more efficient. They are compressing very bigger models. Compressing. What does that mean? What compression technique are they looking at? Wait, where's the method? they pass it. Okay, see. Oh, so this is all. That's it. Oh, so the method is just explained quite compactly. Okay, let's take a look then. Like if the bigger model say 1 million parameters, they want to distill the knowledge into 500, right? But I don't know what distilling means, or rather, what does it, you know, like. So I guess the definition you are trying to say is that I have a 1 million parameter network which delivers some result. What I want to do is to use the 1 million to figure out the parameters for the 500k smaller model and achieve the same result, or you know, allowing some type of you know, maybe not fully the same, but okay, that's an interesting problem. It's a very interesting problem. How do they do it? I mean, that's cool, right? I mean, how do they do it, and how far can you push it? Or rather, is there some theory on it? That would be cool. Okay, let me just take a minute to think about this without reading it first. What does it mean? I mean, it makes sense to say that so okay, naively speaking, the most naive way, you ignore the larger model, you just train a smaller model, and then you know, just train it as usual, and then that's expensive, obviously. So I wonder if this method makes things cheaper or makes things free in the sense that you practically get the smaller model for free, the trained smaller model for free. That would be really impressive. Or maybe it's not completely free, but it should be significantly cheaper than training the small model, or it should be able to allow the small model to perform better than it could, maybe. That would be valuable. And how small can you do? Or rather, what is the relationship between the compression? I can definitely believe that if you have a large model, that a lot of it is not used, a lot of the weights are small and not meaningful, so you can shrink it. But I wait, what do people do that? What do they call it? Pruning? No, pruning? I don't know, is that what they call? Yeah, so you move weights. It's a method of compression, right? Okay. So I'm thinking, is this relevant to pruning? Don't know. Okay, let's read. Okay, softmax. Okay, so I mean, though I'm not an expert, I understand softmax. Converts logic compute each class. Yeah, that's a softmax. Yep. Where T is the temperature. Okay. Softer. Okay. In the simplest form of distillation, knowledge is transferred to a distilled model by training it on a transfer set. What? Wait. Knowledge is transferred to the distilled model, so the smaller model, by training it on what's it? The smaller model on a transfer set, which is, I guess, a specific data set, and using a soft target distribution for each case in the transfer set that is produced. What? Wait, what? I don't understand what the heck. This paragraph is loaded. I do not know what I'm reading. And using a soft target distribution, what does that mean? For each case? Oh, okay, soft as in high temperature. In the transfer set that is produced by using the cumbersome model with higher temperature in its softmax. Is used, the same temperature is used when training the distilled model, but after it has been trained, it uses a temperature of 1. What? I guess I need to know what a transfer set is. So when you soft, what does soft imply? Softer distribution. So I guess I'm not that familiar with softmax after all, because I've never really played with the idea of temperature. What does it correspond to? Yes, a low temperature makes it confident, high makes it less confident. Sure. But what does that, I mean, okay, so you are changing the values by some constant, which is reflected in your exponential term. Sure. Interesting. So when you have high temperature, you are telling your model, you are saying your model will be less confident, so it is more murky. Okay. Not too sure what the goal is for that. Oh, I think I understand what it means. Okay, if my guess is right, it's saying that, so I train my larger model, and my larger model, is able to give me all the outputs, the softmax outputs, and I want the outputs to be in high temperatures so that they are relatively mild, I guess. And then what I do next is to train my smaller network to match that mild output. So essentially I am creating a data set called the transfer set, so that I can easily train the smaller network. and then once you train it, you reduce the temperature to 1. Okay. Alright, let's see if I'm making any sense here. When the correct labels are known for all or some of the transfer set, this method can be significantly improved by training the distill model to produce the correct labels. Okay. One way to do this is to use the correct labels to modify the soft targets. Okay. But we found a better way is to simply use the weighted average of the two objective functions. Oh, convenient. Yeah. The first objective is the cross entropy loss with soft targets, and this cross entropy is computed using the same high temperature as was used for generating soft targets from the Cumberson model. Wait, using the high temperature in the softmax of the distilled model. Wait. The first objective is the cross entropy, and this cross entropy is computed using the same high temperature in the softmax of the distilled model as was used to generating soft targets from the Cumberson model. So I guess the first question I have is also, how do you pick the temperature? Is it just something that you inherit from the problem in the larger model, or you make it large so that it's easy to train? Then it's cross entropy correct labels. This is computed using the exact same logics in the softmax but with a temperature of 1. Okay, so that means you are simultaneously training a normal small network. Okay, okay, we're getting somewhere. It's probably a hyperparameter, right? And I assume that like all things, yes, that is true. Yeah, and I assume that the higher the temperature, the easier it is to train, right? So for example, you can imagine if the temperature is so high that everything comes up to be, if you have Clay classes, your probability is all 1 over K, then you know that term in your objective function is going to be constant, something like that. And then you can't really learn from that soft target. So the softer it is, but then it's easier to learn in the sense that you make it soft. I guess I'm trying to convince myself making sense. Okay, yes, but so far cool. So far, and I think I'm following what's happening. This is computed. Blah blah. We found that the best result generally obtained by using a considerably lower weight on the second objective, meaning the correct label one. Since the magnitudes, so that's one of the things. We found that the best results were generally obtained by using considerably, also misspelled. Is this for real? So this, okay, by low weight. Like, what do I do with that information? As in, maybe it's depending on the problem, maybe it's depending on the model, maybe it's depending on the labels themselves, or the data. I don't know. So when I read things like that, I just go like, okay, cool. It's like super circumstantial. Since the magnitudes of the gradients produced by the soft targets scale as 1 over t square, it is important to multiply t square when using both soft and hard targets. Yes. This ensures that the relative contributions are roughly unchanged if the temperature used is unchanged while experimenting. Sure, yes. Matching logic is a special case of distillation. Mm-hmm. Mm-hmm. Oh, we can do this? What the hell is this? Oh, is it just a 1 plus 1 plus? Yeah, so this is just the standard the standard approximation for the exponential is just 1 plus this. Yeah. Oh, this is so clean. Okay, I mean it's an approximation, but it's clean. So in the high temperature limit, it's equivalent to minimizing. Right. Okay. That's true. Yeah, it's an empirical question. Interesting. Okay, cool. This is an idea that is useful. Let me write that down before I forget. Thanks so much for this recommendation. Let me write down so that I can refer to it. We should train large network, then have a smaller network be trained with a special objective function matching very cool. Don't think it's the same thing, but it might be helpful to think on it. Can you find a parallel in statistics? I've heard of student teacher distribution. What? Student teacher? Do you mean like in learning theory, or do you mean like student T distribution? The student T distribution, but I don't know if there's students distribution. What is this? I think you mean students T distribution, or it could be like teacher is a method in supervised learning, right? Semi-supervised learning, the mean teacher method, right? Oh my god, I just googled mean teachers come out. Yeah. So like mean teacher, it's a model. Like, can you find parallel analogy in the technique in stats? I guess the most obvious technique is just conditioning. So I'm pretty sure that this distillation technique can be formulated in terms of a statistical viewpoint. But if you're talking about a method that exists in stats based on this type of transfer learning idea, yeah, I mean, I guess the spirit of it is encapsulated in just general Bayesian type of methods where you condition on what you know already, and then you can train other things. But you will need a model for that. That's a thing, yeah. So yeah, and you have to phrase everything with a distribution. Yeah, so I don't think I know exactly clear methods. Yeah, but I guess like I don't know. I guess conditioning is it's a very very general, just a general idea, but it is very very applicable here. Okay, cool. Very 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 cool. I don't even remember what I'm reading anymore. Do I even really care anymore? I don't know. What time is it? It's 11. Okay, let's just quickly breeze through this. I think I might just do my master's thesis on this topic. Seems isolated and cool enough. Yeah, I mean, it's a really cool idea, but I'd be interested to see what people have done with it. Maybe it's not the most hype idea because maybe it's a bit methodological and it's not just spamming thicker and deeper networks. But yeah, I'm be interested to see what people are doing with this. Pretty sure this can't be the state of the art like that paper. It's just a very basic description on the MNIST data set where anything works on MNIST, right? I mean, yeah. Okay, I'm gonna go to the washroom real quick. What did I miss? Definitely a lot to think about. Billion plus parameter networks are getting more and more common. If there's a way to distill that into smaller models, it would be a game changer. Yeah, it will help in deployment. That's the thing, right? Yeah, I guess it depends on how well you can distill it, because like let's say wait, in my internship we were using transformers for a question answering model, and it takes so long for inference on CPU. Right, yeah. So I feel like the most obvious approaches, so let's say it's too long or too expensive to run. Clearly the main approach is, I really like the idea of distillation, by the way, but it's a very attractive idea from a theoretical standpoint, right? You're trying to learn you're trying to learn a simpler representation of a more complex decision process. I think that's super cool. But on the other hand, there will be people working on how to make CPUs faster, right? Or how to make computation more efficient on CPU to overcome this overhead. So yeah, not sure which is gonna prevail. I suspect, theoretically speaking, it's much harder to do distillation because you're gonna take time to develop the methods, whereas people can just dive straight into parallel computing. Think about how to break down your network into a few pieces, run them all on GPUs. I don't know, smart way of storing things. Yeah. But yeah, I mean, you're definitely right that if you solve the cost problem of large networks, that's gonna be impressive. You're saying it will be obsolete after a few years? No. What do you mean with faster CPUs? No. I mean, methods come and go in terms of popularity, but once you've learned something and developed something, and then I think that's very useful already, because it's gonna be used for further development by other people anyway. So that's very good. In terms of whether it's useful, I don't know. Yeah, it could be that CPUs develop in a way that makes it obsolete. That's possible, that's possible, I guess, but I don't know. I wouldn't worry about it really. Yeah. I mean, on the other hand, let's say you develop something super cool, some super smart way of doing parallel computing that's very intricate, with the current architecture, and then much better CPUs come in and destroying the speed. Then no one's gonna bother with the complicated parallelism, cross-architectural, whatever crazy stuff, right? Then that would be obsolete, I would say. What's this? Incomplete ideas, bitter lesson in research. What the heck is this? Whoa. Wait, let me try to quickly read this. This is quite short. Oof, this is exactly relevant. Yes. Okay, I don't know if y'all can see this, if I was reading the stream. Yeah, but it's basically saying that humans like to explore knowledge, and enjoy making things complicated, and sometimes that's not what's useful. Sometimes what's useful is just to get your simple basic things done really really fast using computers. And yeah, I guess that's true. It could be that it could be that theories don't really matter that much anymore when it comes to these type of application. You just throw compute at it and then it solves itself. Could be. There's some nice theory describing that as well, but no one needs to really care about that, I think. Yeah, it works. For people who only care about results, right? Then you just care about the results. Don't need to think. Maybe I don't completely agree. I think domain knowledge complements a bit more than articles suggest. Maybe I'm just biased. I guess it depends on the problem, right? It depends on data ultimately, right? Like, if we have a lot of data, then we really don't need to know much, but there are definitely still so many things where we can't have data. And so there's still a lot of room for domain knowledge. Like recently I saw this Tom Scott video about language, about how computers are still far away from understanding human language because they don't understand context, they don't understand the way words work. What's the Tom Scott video again? Let me go find it out. Now that there's this linguist who come up with a set of sentences that are chosen to confuse computers, but not humans, and like any human would be able to read it with no problem, but computers are gonna have a large problem. Oh no, I don't remember. It's not a new video as well. This one. What's it called? There's a name for it.
The Winograd schema.
The Winograd schema, yes. Yeah, so things like this, okay, well, maybe not specifically things like this, but so for example, this the city councilman refused the demonstrators a permit because they feared violence. So who feared violence? Any human would be able to say, of course. It's these guys, right? Yeah. But a computer would have no idea, right? Because it needs to understand the relation between councilmen and demonstrators. It needs to have a pre-existing notion of what demonstration can be like, what a permit is, I guess, and how it relates to violence, and have a notion of violence. So these type of thing, humans gonna own this, right? No machine can properly have enough intuition to understand such things that come so naturally to us. Yeah. So yeah, in such cases, and there's many more of such examples, we are still far away from being able to just have enough data to do any of these things. Chomsky had one, right? Yeah. I'm sure Noam Chomsky had very good ideas about that as well. Is he alive? Is Noam Chomsky alive? I think he is. He's just old. Okay, he's 92. Shoot, yeah. Noam Chomsky. Okay, let us continue. What was I reading again? Jeez. Yes. Use a predictive posterior condition on I to approximate the log likelihood. So this is similar to the conditioning that I showed in my other code. Define the first stage as this. I don't really want to read this expression, but okay, so it's similar to an MH style, where this is the prior, I assume. Is P the prior? Did they say? I assume it's the prior. So prior and likelihood. It's basically what it is. So this is the posterior, basically, like the surrogate posterior, if you will. And then the acceptance probability depends on. Sure. This is the most important part. A key part of our approach involves marginalizing the dependence. How did he do that? Mm-hmm. What? 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 Wait, this is. So you're using the mean. By assumption 1, we have k equals 0. Therefore, it's just this. So you remove the dependence of the acceptance probability on LL. Huh. What? Wait, I'm confused. What? But you are writing it in terms of mu and k, right? Are you not? And isn't this gonna be 0? I'm confused. Why is this term here? Oh, it's 0 evaluated at k. This is the proposal, so it's not 0. Lostness. I'm lost. Where u is equals to the exact log posterior. Right, exactly. So it can be seen that depends on the GP variance, and therefore acceptance point is larger in regions where GP is uncertain. The acceptance is larger in regions where it's uncertain. Similar to the acquisition function in optimization, this naturally results in exploration trade-off. We aim to sample from the target. Given for stage 1, we accept with probability this, otherwise this defines the following transition kernel. You accept with this, and then you stay where you are. If you reject, one can show that the above transition kernel satisfy detailed balance. I believe that. We are not interested in the approximated. This is the reason we perform the second stage. Yes, so it's detailed balance, but then it's detailed balance for this. We perform another MH step evaluating the exact log likelihood. Denote the point sampled. Denote that is either equals to or the of k fields rejected. Wait, does this work? This works? Huh? Okay, I guess I need to read the proof more carefully if I want to be convinced. The definition of Q star means a rejection in stage 1. always lead to rejection at stage 2. Yes. So we do not compute 6 if we reject already. Yeah. When the sample is accepted, we compute the full and evaluate. Overall, the acceptance probability for new point is this. The overall two-stage preserves detailed balance with respect to the posterior. Okay, I can't really see this just yet, but I mean, I guess the proof will give more about this. Dude, it's the same song again. What the freak? I swear I chose a different. Oh my god, this is so creepy. Okay. Completely different mix. Oh man. Okay. I'm gonna go out to dinner. See ya. Enjoy in my stay. Thank you so much for the recommendations. I learned a lot. Cool. And enjoy your dinner. Have a good evening yourself. Cool rap, but not the best for reading. Yes. Let's try to read with this music. I don't know. The overall two-stage preserve detailed balance with respect, and this follows directly from 6, which is a standard MH with proposal. Oh. I guess. What am I looking at? I don't even. What am I looking at? GP mean. Okay. As you have more and more convergence. Oh, okay. So it's a. So I should read it like a. I should read it like a, like an animation, right? So this is the first screen, second frame, third frame. What the hell is this? 0 to 1. Ah. Why they plot it on the same? Okay, I guess. Yeah, that makes sense because every time you evaluate it, every time you add a point, you are doing a full evaluation. That means you should accept it, right? That's why you have it in the first place, because you accepted it. Okay. Oh wow. This is a fancy tune. What's this genre? Drum and bass? Drum and bass. Alright, let's try something else that's less intense. Yeah, okay, now I'm convinced that they all the... Yeah. These are all different long playlists I'm using, and they are all using the same songs. It's just ridiculous. Okay. Wow, look at this. Wait, this yield better ESS? But is it significant? But it's cheaper lah. Right, so if it's T3 I see. 15%. But how does it say that? I mean, okay, this is a nice idea. I like it. But again, the main argument is that likelihoods are expensive to compute, and this method can save on that. But then here in their experiments, in these 5 problems, very fast. So I would like to see how it really performs in problems where evaluating livelihood is expensive, and then using this method you get something fast, right? That would be valuable. Don't know. Yeah, see, this is another thing. We have used a full GP whose computational grows cubically as the size of the training set increases. That's right, that's what I was talking about. Because every time you have your matrix gets larger and larger, which is just funny. When it is necessary to sample thousands of samples, but thousands of samples is incredibly pedestrian, right? Cool. Let me just interesting idea. Interesting idea. How long have we been live? 2 hours? Alright, let's hmm. 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 Oh my god, I'm gonna share this with a buddy of mine. Hmm. This is a interesting read. I highly recommend it for everyone. It's called The Bitter Lesson by Richard Sutton. It's about the development of I guess these types of intelligence, so-called intelligence algorithms and methods, and the interplay between building more sophisticated method, using our human ingenuity versus relying on simpler ideas, but performs at scale, right? So do things fast and many times. Sometimes can be quite useful and more useful than trying to engineer some type of human, so-called human knowledge. So one of the examples mentioned here is the idea of vision, which is cool. So in the early days of vision, when we look at, let's say we're trying to identify a road and a sidewalk, for example. Oh, what's happening? Yeah, like a road and a sidewalk, it would make sense when a human look at it to say that, okay, so there's a road, it's this color, then there's the edge, and then it goes to the sidewalk that's of a different color, maybe, or different material, and we can see it. And then so what is the difference between the two? Okay, cool, maybe you look at the edge, right? So you detect this edge where the two meet, and then you say, okay, so one is one and the other is the other. So that's a very so when we try to program that, it is that we're trying to incorporate what we think is how human perceive, right? They say, oh, we notice the edge, and that's how we so it is a manifestation of how we think, which is what is mentioned here. But all those methods are now gone. All those very fancy methods, they're gone. Now we are just revolving around neural networks that uses convolutional neural networks, and yeah, those methods work far better. And those notions have those ideas have no sense of no sense of detecting an edge intentionally, or trying to understand what a road is, or it doesn't really try to do that. It just tries to look at it from a completely different mechanical, computational viewpoint. And people don't like that, I guess, some people, but it works. And then he makes a very good point here in the last paragraph, saying that we should not, like, the way our mind works and the way we perceive reality is so incomprehensibly complex that we should not try to think that we can understand it and then shoehorn it into an algorithm. Instead, what we should do is to build simpler methods, not say simpler, but I guess more obvious things to do that can help the algorithm learn on its own, right? So it says here I can't see it here, but it says we should build meta methods that can find and capture this arbitrary complexity. Yeah. So, and in fact, the more we try to forcefully input what we think is the human touch, right, how we perceive, we want AI agents to discover, like, we can not which contain what we have discovered. Important point, and building in our discoveries only makes it harder to see how the discovering process can be done. Whoa. Painful read for people who's been working on this half their life, but well, such is life. Have I digested my dinner? More or less. I should go for a run soon. Don't really feel like running today though. Okay, run. Are you enjoying this music? Something something. I think this is called city pop. I've heard of this genre several times. Oh, it's called future funk here, but I'm pretty sure it's under city pop. Oh, this is the best, right? I mean, I don't hate this. I mean, there's an occasion for this music, I suppose, but on its own, I don't hate it. Oh, city pop. Let's go. City pop. Are you gonna get up and dance? I had to change the music. Yeah, sounds like house. Oh, this is so bomb. This is good. It's like oldie but with a touch more funk. Sounds like house. This is not house. Let me show you house music. This is house. This is house. Oh, okay. This is not really house either, I guess. But I guess I don't know enough. Oh yeah, this is house. Yes, this is. Yep. Oh, very house indeed. Actually, it helps concentrating. It's not so bad. There's a rhythm to it. Maybe it's a good running tune as well, actually. Possible. Should I try to read this paper? I'm pretty saturated right now, but I feel like it can do me good really to understand this paper. Or at least understand, wait, what the heck? I'm trying to see section 2. Oh, section 1 is a lot. Okay, let's just read section 1, okay? Let's just read section 1. Why is there 2 people on the stream? Am I one of them? No, I'm not. Yeah, if you join the stream, if you subscribe or if you follow or if you, I don't know what's follow, subscribe. Then if I reach certain number, then you get my videos stay on my page for much longer. Yeah, so far you can also view the older streams on my YouTube, which is just me putting the videos there because they expire on Twitch. So yeah. So yeah, if you want to see older videos, then you can subscribe and we eventually get there. I don't know how many subscribers I have. I don't know, 10? 20? How many do I have actually? So that's a very good question. I'm guessing like 15? Something like 15? How do I even check? Maybe if I know how to check, right, I would have a better idea of what the hell I'm doing. I have no idea. How do I check how many people what do you call it? What do I call my people? Subscribers? I have 19 followers. Okay. And I have 6 followers in the last month. Alright. 19. Alright. Cool. Alright guys, subscribe, follow, let's hit that 20 this month, yo. Yeah, we're gonna get there. And wait, how many do I need to reach the next, I don't know, tier? 50, what the heck? I need 50. So I'm not even halfway there. Oh no, if I have 50 then VIP status to mom. What does that even mean? Oh. Okay. So if I have 50 followers, then I can grant my followers VIP status. I don't know what that does, but Twitch is complicated. The only reason that I care for things to stay on the stream is so that people can see if they help, that's all. If that helps. A playlist that might interest you. Sophia just shared a playlist. Yes. Wait, what do you mean? Oh dear. Oh dear. Okay. Yeah, when you're tired and feel like just stopping, this is when you should push. This is when you should push. Okay, let's push. Let's just finish this section. Go for a run. Think about what I read during the run. Probably fall down. And then come back and finish it, maybe. Okay. Okay. I've never used this word or actually really seen it before. Aforesaid. Aforementioned, yes. Aforesaid. That's cool. Wait, what's the idea here? Sequentially comparing parts of the MCMC acceptance ratio to independent uniforms in order to stop earlier the computation of the ratio, namely as soon as one term is below the corresponding uniform. So as soon as one term is below, then you accept? No. Wait, I don't understand. Of course I don't. Mm-hmm. What? Okay. And then accept the move with probability so this value will be between, oh no, it could be larger than 1, but the point is that okay, so right, so the moment this value is smaller than 1, this whole term will be smaller than 1, obviously. It's just going to be this value, and the multiplication of it is going to be that value or smaller than 1 as well, because the whole thing is the maximum is 1. So I guess the moment one value falls below this, oh okay, wait, in practice sequentially comparing those probabilities. Yo, I like this track. What's this song? So how is this delaying acceptance? So you only accept when all of them are smaller? But when you do them sequentially, isn't that expensive too? I don't know. Wait, I want to make sure I understand this correctly. So it's saying that accept the move with probability Wait a second. So it's saying that for a step that would have been accepted, everything would be larger than 1, so we would accept all of it. And for a step that is rejected, we may not need to compute everything before we reject it. Is that what it's saying? So because if we compute the product of all the uniform variates, since they're all between 0 and 1, if it's rejected, no, that's not true. I don't understand. Oh my god, I'm tired. Okay, so my notion of delay acceptance is completely wrong. It's not that you accept it and then you do more. Is that you... I shouldn't call it delay acceptance, right? It should be called early rejection, right? Maybe I'm not understanding things correctly. Yeah, I think delayed acceptance is a really confusing way to describe it. I would just call it early rejection so that you don't waste your time computing the full Metropolis Hastings acceptance ratio. Alright, but the probability is going to be lower than the original. So you sacrifice a little bit lah. I mean, of course that makes sense. Otherwise, you just do it all the time. Yeah, this is important. Okay. Hmm. Okay, cool. Yeah. Let me just check one last thing. Hmm. I see. So that's what it means. Okay, that's interesting. Alright, so today I read a bit about delayed acceptance, a little bit about distillation, a bit about using GPs, this GP enhanced two-stage algorithm, and then a bit about genetically modified jumping MCMC that I don't really understand that much. But yeah, so that's cool. Alright, cool. I'm gonna check out now. Alright, see you guys.